What I'd like to do today is continue our discussion of supervised learning. So last Wednesday, you saw the linear regression algorithm, including both gradient descent, how to formulate the problem, then gradient descent, and then the normal equations. What I'd like to do today is talk about locally weighted regression, which is a way to modify linear regression to make it fit very nonlinear functions, so you aren't just fixed straight lines. And then we'll talk about probabilistic interpretation of linear regression, and that will lead us into the first classification algorithm you see in this class called logistic regression. And we'll talk about an algorithm called Newton's method for logistic regression. And so the dependency of ideas in this class is that locally weighted regression will depend on what you learned in linear regression. And then we're actually going to just cover the key ideas of locally weighted regression and let you play with some of the ideas yourself in the problem set 1, which will release later this week. And then I guess give a probabilistic interpretation of linear regression. Logistic regression will depend on that. And Newton's method is for logistic regression. Okay. To recap the notation you saw on Wednesday, we used this notation xi comma yi to denote a single training example where xi was n plus 1 dimensional. So if you had two features, the size of a house and the number of bedrooms, then xi would be 2 plus 1, would be 3-dimensional, because we had introduced a new sort of fake feature, x0, which was always set to the value of 1. And then yi, in the case of regression, is always a real number. N was the number of training examples, n was the number of features, and this was the hypothesis, right? It's a linear function of the features x, including this feature x0, which is always set to 1. And j was the cost function you would minimize. You minimize this as a function of j to find the parameters theta for your straight line fit to the data. Okay, so that's what you saw last Wednesday. Now, if you have a data set that looks like that, where this is the size of a house and this is the price of a house, what you saw on Wednesday, last Wednesday, was an algorithm to fit a straight line, right, to this data. So the hypothesis was of the form theta 0 plus theta 1 x, or theta 1 x1, right, same thing. But with this data set, maybe it actually looks, maybe the data looks a little bit like that. And so one question that you have to address when fitting models to the data is, what are the features you want? Do you want to fit a straight line to this problem, or do you want to fit a hypothesis of the form theta 1 x plus theta 2 x squared, since this may be a quadratic function? Right. Now the problem with quadratic functions is that a quadratic function eventually starts, curving back down, or that would be a quadratic function that starts curving back down. So maybe you don't want to fit a quadratic function. Instead, maybe you want to fit something like that. If housing prices sort of curve down up a little bit, but you don't want it to eventually curve back down the way a quadratic function would, right? And if you want to do this, the way you would implement this is you define the first feature x1 equals x, and the second feature x2 equals x squared, or you define x1 to be equal to x and x2 equals square root of x, right? And by defining a new feature, x2, which can be the square of x or square root of x, then the machinery that you saw from Wednesday of linear regression applies to fit these types of functions to the data. So later this quarter, you'll hear about feature selection algorithms, which is a type of algorithm for automatically deciding, do you want x squared as a feature, or square root of x as a feature, or maybe you want log of x as a feature, right? But what set of features does the best job fitting the data that you have if it's not fit well by a perfectly straight line? What I'd like to do today is, so you hear about feature selection later this quarter. What I want to share with you today is a different way of addressing this problem of what if the data isn't just fit well by a straight line. And in particular, I want to share with you an idea called locally weighted regression, or locally weighted linear regression. So let me use a slightly different example to illustrate this, which is that, if you have a data set that looks like that, right? So it's pretty clear what the shape of this data is, but how do you fit a curve that kind of looks like that, right? And it's actually quite difficult to find features. Is it square root of x, log of x, x cubed, like third root of x, x to the power of 2/3? But what is the set of features that lets you do this? So we'll sidestep all those problems with an algorithm called locally weighted regression. And to introduce a bit more machine learning terminology, in machine learning, we sometimes distinguish between parametric learning algorithms and non-parametric learning algorithms. But in a parametric learning algorithm, there's you fit some fixed set of parameters, such as theta I to data. And so linear regression, as you saw last Wednesday, is a parametric learning algorithm because there's a fixed set of parameters, the theta i's that you fit to data, and then you're done, right? Locally weighted regression will be our first exposure to a non-parametric learning algorithm. And what that means is that the amount of data / parameters you need to keep grows, and in this case it grows linearly. With the size of the data, with the size of the training set. Okay? So with a parametric learning algorithm, no matter how big your training set is, you fit the parameters theta I, then you could erase the training set from your computer memory and make predictions just using the parameters theta I. In a non-parametric learning algorithm, which we'll see in a second, the amount of stuff you need to keep around in computer memory, or the amount of stuff you need to store around, grows linearly as a function of the training set size. And so this type of algorithm is, it may not be great if you have a really, really massive data set because you need to keep all of the data around, in computer memory or on disk just to make predictions. Okay, so, but we'll see an example of this. And one of the effects of this is that it'll be able to fit that data that I drew up there quite well without you needing to fiddle manually with features. And again, you get to practice implementing locally weighted regression at homework. So I'm going to go over the high-level ideas relatively quickly and then let you gain practice in the problem set. All right, so let me redraw that data set. Maybe something like this. Well, all right, so say you have a data set like this. Now, for linear regression, if you want to evaluate h at a certain value of the input, right? So to make a prediction at a certain value of x, for linear regression, what you do is you fit theta, to minimize this cost function. And then you return theta transpose x, right? So for the straight line, and then if you want to make a prediction at this value x, you then return theta transpose x. For locally weighted regression, you do something slightly different, which is, if this is the value of x and you want to make a prediction around that value of x, what you do is you look in a little local neighborhood at the training examples close to that point x where you want to make a prediction. And then I'll describe this informally for now, but we'll formalize this in math in a second. But focusing mainly on these examples and looking a little bit at further out examples, but really focusing mainly on these examples, you try to fit a straight line like that, focusing on the training examples that are close to where you want to make a prediction. And by close, I mean the values are similar on the x-axis. The x values are similar. And then to actually make a prediction, you will use this green line that you just fit to make a prediction at that value of x. Okay? Now, if you want to make a prediction at a different point, let's say that the user now says, hey, make a prediction for this point. Then what you would do is focus on this local area, kind of look at those points. And when I say focus, say, put most of the weight on these points, but you kind of take a glance at the points further away, but most of the attention is on these. Fit a straight line to that, and then you use that straight line to make a prediction. Okay? And so to formalize this, in locally weighted regression, you will fit theta to minimize a modified cost function where Wi is a weight function and so the default choice, a common choice of Wi will be this. Right? I'm going to add something to this equation a little bit later. But Wi is a weighting function where, notice that this formula has the following property, right? If xi minus x is small, then the weight will be close to 1, because if xi and x, so x is the location where you want to make a prediction, and xi is the input x for your I training example. So Wi is a weighting function. There's a value between 0 and 1 that tells you how much should you pay attention to the values of xi comma yi when fitting, say, this green line or that red line. And so if xi minus x is small, so if that's a training example that is close to where you want to make the prediction for x, then this is about e to the 0, right? E to the negative 0 if the numerator here is small, and e to the 0 is close to 1, right? And conversely, if xi minus x is large, then Wi is close to 0. And so if xi is very far away, so let's say you're fitting this green line, and this is your example, xi, yi. Then it's saying, give this example all the way out there if you're fitting the green line, right? If you're looking at this first x, saying that example should have a weight very close to 0. Okay? And so if you look at the cost function, the main modification to the cost function we've made is that we've added this weighting term, right? And so what locally weighted regression does is saying, if an example xi is far from where you want to make a prediction, multiply that error term by 0, or by a constant very close to 0. Whereas if it's close to where you want to make a prediction, multiply that error term by 1. And so the net effect of this is that this is summing, if the terms multiplied by 0 disappear, right? So the net effect of this is that this sums over essentially only the terms for the squared error for the examples that are close to the value of x where you want to make a prediction. Okay? And that's why when you fit theta to minimize this, you end up paying attention only to the points, only to the examples close to where you want to make a prediction, and fitting a line like the green line over there. Okay? So let me draw a couple more pictures to illustrate this. So let me draw a slightly smaller data set just to make this easier to illustrate. So that's your training set. So that's examples x1, x2, x3, x4. And if you want to make a prediction here, right, at that point x, then this curve here looks, the shape of this curve is actually like this. Right? And this is the shape of a Gaussian bell curve, but this has nothing to do with a Gaussian density, right? So this thing does not integrate to 1. So just sometimes people ask, well, is this using Gaussian density? The answer is no. This is just a function that is shaped a lot like a Gaussian, but Gaussian densities, probability density functions have to integrate to 1, and this does not. So there's nothing to do with a Gaussian probability density. Question? Oh, sure. How do you choose the word? Let me get back to that. Yeah. And so for this example, this height here says give this example a weight equal to the height of that thing. Give this example a weight equal to the height of this, height of this, height of that. Right? Which is why if you have an example that's way out there, is given a weight that's essentially 0, which is why it's weighting only the nearby examples when trying to fit a straight line, right? For making predictions close to this. Okay. Now, so one last thing that I want to mention, which is the question just now, which is how do you choose the width of this Gaussian density, right? How fat is it? Or how thin should it be? And this decides how big a neighborhood should you look in order to decide what's the neighborhood of points you should use to fit this local straight line. And so for a Gaussian function like this, I'm going to call this the bandwidth parameter tau. Right? And this is a parameter or hyperparameter of the algorithm. And depending on the choice of tau, you can choose a fatter or thinner bell-shaped curve, which causes you to look in a bigger or a narrower window in order to decide how many nearby examples you use in order to fit this straight line. Okay? And it turns out that, and I want to leave you to discover this yourself in the problem set. If you've taken a little bit of machine learning elsewhere, heard of the terms test is on? Okay, good. We're still on. Good. It turns out that the choice of the bandwidth tau has an effect on overfitting and underfitting. If you don't know what those terms mean, don't worry about it. We'll define them later this quarter. But what you get to do in the problem set is play with tau yourself and see why if tau is too broad, you end up fitting you end up over-smoothing the data, and if tau is too thin, you end up fitting a very jagged fit to the data. And if any of these things don't make sense yet, don't worry about it. They'll make sense after you play with it in the problem set. Okay. So yeah, since you play with the varying tau in the problem set and see for yourself the net impact of that. Okay. Question? Thank you. This is tau squared. Yeah. What happens if you need to infer the value of h outside the scope of the data set? It turns out that you could still use this algorithm. It's just that its results may not be very good. Yeah, it depends, I guess. Locally weighted linear regression is usually not great at extrapolation, but then many learning algorithms are not great at extrapolation. So all the formulas still work. You still implement this, but yeah, you can also try it in your problem set and see what happens. Just one last question.
Is it possible to have like a variable tau depending on if some parts of your data have lots of
Yes, this is possible. The variable tau depend on yes, it is, and there are quite complicated ways to choose tau based on how many points there are in the local region and so on. Yes, there's a huge literature on different formulas. Actually, for example, instead of this Gaussian bump thing, sometimes people use that triangle shape function, so it absolutely goes to 0 upside some small range. So there are many versions of this algorithm. So I tend to use locally weighted linear regression when you have a relatively low dimensional data set. So when the number of features is not too big, right? So when n is quite small, like 2 or 3 or something, and we have a lot of data, and you don't want to think about what features to use, right? So that's the scenario. So if you actually have a data set that looks like these I've been drawing, locally weighted linear regression is a pretty good algorithm. Right? All right, maybe just one last question, then we'll move on.
Since you have a lot of, when you have a lot of data, wouldn't this usually computationally expensive since you're looking at every data point?
Oh, sure. Yes, if you have a lot of data, won't this be computationally expensive? Yes, it would be. I guess a lot of data is relative. Yes, but you have 2, 3, 4 dimensional data and hundreds of examples, or maybe thousands of examples. It turns out the computation needed to fit the minimization is similar to the normal equations, and so it involves solving a linear system of equations of dimension equal to the number of training examples you have. So if that's like 1,000 or a few thousand, that's not too bad. If you have millions of examples, then there are also more sophisticated algorithms like KD trees and much more complicated algorithms to do this when you have millions or tens of millions of examples. Yeah. Okay, so really, you get a better sense of this algorithm when you play with it in the problem set. Now, the second topic, so I'm going to put aside locally weighted regression. We won't talk about that set of ideas anymore today, but what I want to do today is on last Wednesday, I had said that I had promised last Wednesday that today I'll give a justification for why we use the squared error, right? Why the squared error? Why not, to the 4th power or absolute value? And so what I want to show you today now is the probabilistic interpretation of linear regression. And this probabilistic interpretation will put us into good standing as we go on to logistic regression today, and then generalized linear models later this week. Okay. Maybe I'll keep the notation there so you can continue to refer to it. So, right, so why least squares? Why squared error? I'm going to present a set of assumptions under which least squares using squared error falls out very naturally, right? Which is, let's say for housing price prediction, let's assume that there's a true price of every house yi, which is x transpose theta I plus epsilon I, where epsilon I is an error term that includes unmodeled effects, and just random noise. Okay? So let's assume that the way housing prices truly work is that every house's price is a linear function of the size of the house and number of bedrooms, plus an error term that captures unmodeled effects, such as maybe one day that seller's in an unusually good mood or an unusually bad mood, and so that makes the price go higher or lower, and we just don't model that, as well as random noise, right? Or maybe don't model the school district, just didn't capture that as one of the features, but other things have an impact on housing prices. And we're going to assume that epsilon I is distributed Gaussian with mean 0 and covariance sigma squared. So I'm going to use this notation to mean, so the way you read this notation is epsilon I, this twiddle you pronounce as is distributed, and then script n paren 0 comma sigma squared. This is a normal distribution, also called the Gaussian distribution. Same thing, normal distribution and Gaussian distribution mean the same thing. The normal distribution with mean 0 and variance sigma squared. Okay? And what this means is that the probability density of epsilon I this is the Gaussian density, 1 over root 2 pi sigma e to the negative epsilon I squared over 2 sigma squared. Okay. Oh, and unlike the bell-shaped curve I used earlier for locally weighted linear regression, this thing does integrate to 1, right? This function integrates to 1 And so this is a Gaussian density. This is a probability density function. Okay? And this is the familiar, Gaussian bell-shaped curve with mean 0 and variance sigma squared, right? Where sigma kind of controls the width of this Gaussian. Okay? And if you haven't seen Gaussians for a while, we'll go over some of the probability prereqs as well in the classes Friday discussion sections. So in other words, we assume that the way housing prices are determined is that first is a true price, theta transpose x, and then some random force of nature, right? The mood of the seller, or I don't know, I don't know, other factors, right? Perturbs it from this true value, theta transpose x I. And the huge assumption we're going to make is that the epsilon i's, these error terms, are IID. And IID from statistics stands for independently and identically distributed. And what that means is that the error term for one house is independent as the error term for a different house, which is actually not a true assumption, right? Because if one house's price on one street is unusually high, probably a price on a different house on the same street will also be unusually high. And so, but this assumption that these epsilon i's are IID stands for independently and identically distributed is one of those assumptions that is probably not absolutely true, but may be good enough that if you make this assumption, you get a pretty good model. Okay? And so, let's see. Under this set of assumptions, this implies that the density or the probability of yi given xi and theta, this is going to be this. Okay, and I'll take this and write it another way. In other words, given x and theta, what's the density, what's the probability of a particular house's price? Well, it's going to be Gaussian with mean given by theta transpose x, I, or theta transpose x, and variance given by sigma squared. Okay? And so, because the way that the price of a house is determined is by taking theta transpose x, which is the quote true price of the house, and then adding noise or adding error of variance sigma squared to it. And so the assumptions on the left imply that given x and theta, the density of y has this distribution, which is really this is the random variable y, and that's the mean, right? And that's the variance of a Gaussian density. Okay. Now, two pieces of notation I want that you should get familiar with. The reason I wrote a semicolon here is that the way you read this equation is the semicolon should be read as parameterized as. Right? And so, because the alternative way to write this would be to say P of xi given P of y given xi comma theta. But if you were to write this notation this way, this would be conditioning on theta. But theta is not a random variable, so you shouldn't condition on theta, which is why I'm going to write a semicolon. And so the way you read this is the probability of yi given xi and parameterized by theta is equal to that formula. Okay. If you don't understand this distinction, again, don't worry too much about it. In statistics, there are multiple schools of statistics called Bayesian statistics and frequentist statistics. This is a frequentist interpretation. For the purposes of machine learning, don't worry about it. But I find that being more consistent with terminology prevents some of our statisticians' friends from getting really upset. But so I'll try to follow statistics convention. So because just don't need unnecessary flack, I guess. But for practical purposes, it's not that important. If you get this notation wrong in your homework, don't worry about it. We won't penalize you. But I'll try to be consistent. But this just means that theta in this view is not a random variable. It's just theta is a set of parameters that parameterizes this probability distribution. Okay. And the way to read the second equation is when you write these equations, you usually don't write them with parentheses. But the way to parse this equation is to say that this thing as a random variable, the random variable y given x and parameterized by theta, this thing that I just drew in green parentheses is distributed Gaussian with that distribution. Okay? Right. All right. Any questions about this? Okay. Cool. So it turns out that if you are willing to make those assumptions, then linear regression falls out almost naturally of the assumptions we just made. And in particular, under the assumptions we just made, the likelihood of the parameters theta, so this is pronounced the likelihood of the parameters theta, L of theta, which is defined as the probability of the data, right? So this is probably of all the values of y, of y1 up to ym, given all the x's and given the parameters theta, parameterized by theta. This is equal to the product from I equals 1 through m of p of yi given xi parameterized by theta. Because we assume the examples were, because we assume the errors are IID, right, that the error terms are independently and identically distributed to each other. So the probability of all of the observations of all the values of y in your training set is equal to the product of the probabilities because of the independence assumption we made. And so plugging in the definition of p of y given x parameterized by theta that we had up there, this is equal to product of that. Okay. Now, again, one more piece of terminology. Another question about now is if you say, hey, Andrew, what's the difference between likelihood and probability, right? And so the likelihood of the parameters is exactly the same thing as the probability of the data. But the reason we sometimes talk about likelihood and sometimes talk about probability is we think of likelihood. So this is some function, right? This thing is a function of the data as well as a function of the parameters theta. And if you view this number, whatever this number is, if you view this thing as a function of the parameters holding the data fixed, then we call that the likelihood. So if you think of the training set, the data is a fixed thing, and then varying parameters theta, then I'm going to use the term likelihood. Whereas if you view the parameters theta as fixed and maybe varying the data, I'm going to say probability, right? So you hear me use, well, I'll try to be consistent. I find I'm pretty good at being consistent, but not perfect. But I'm going to try to say likelihood of the parameters and probability of the data, even though those evaluate to the same thing. It's just, for this function is a function of data and the parameters. Which one are you viewing as fixed and which one are you viewing as variable? So when you view this as a function of theta, I'm going to use the term likelihood. So hopefully you hear me say likelihood of the parameters. Hopefully you won't hear me say likelihood of the data, right? And similarly, hopefully you hear me say probability of the data and not probability of the parameters. Okay? Okay. Yeah. Likelihood of parameters. Okay, so probability of the data? No. Wait. Oh, theta, got it. Sorry, yes, likelihood of theta, got it. Yes. Sorry, yes, likelihood of theta, that's correct. No, so theta is a set of parameters. It's not a random variable. So likelihood of theta doesn't mean theta is a random variable. Right, cool, yeah, thank you. By the way, the stuff about what's a random variable and what's not, the semicolon versus comma thing, we explained this in more detail in the lecture notes. To me, this is part of, you know, a little bit paying homage to the religion of Bayesian frequencies versus Bayesian Bayesians in statistics. From applied machine learning, operational, what you write code point of view, it doesn't matter that much. Yeah, but theta is not a random variable. We have likelihood of parameters, which are not a random variable. Yeah, go ahead. What's the rationale for choosing? Oh, sure. Why is epsilon I Gaussian? Turns out because of central limit theorem from statistics, most error distributions are Gaussian, right? If there's an error that's made up of lots of little noise sources which are not too correlated, then by the central limit theorem, it will be Gaussian. So if you think that how the noise perturbations are, the mood of the seller, what's the school district, you know, what's the weather like, access to transportation, and all of these sources are not too correlated, and you add them up, then the distribution will be Gaussian. And I think, well, yeah. So really, because of the central limit theorem, I think the Gaussian has become a default noise distribution. But for things where the true noise distribution is very far from Gaussian, this model does do less well. And in fact, when you see generalized linear models on Wednesday, you see how to generalize all of these algorithms to very different distributions like Poisson and so on. Okay. All right. So we've seen the likelihood of the parameters theta. So I'm going to use lowercase l to denote the log likelihood. And the log likelihood is just the log of the likelihood. And so, well, just... Right. And so log of a product is equal to the sum of the logs, right? And so this is equal to and so this is n log 1 over root. Okay. And so one of the well-tested methods in statistics for estimating parameters is to use maximum likelihood estimation, or MLE. Which means to choose theta to maximize the likelihood, right? So given a data set, how would you like to estimate theta? Well, one natural way to choose theta is to choose whatever value of theta has the highest likelihood. Or in other words, choose the value of theta so that that value of theta maximizes the probability of the data, right? And so to simplify the algebra, rather than maximizing the likelihood, capital L, it is actually easier to maximize the log likelihood. But the log is a strictly monotonically increasing function, so the value of theta that maximizes the log likelihood should be the same as the value of theta that maximizes the likelihood. And if you derive the log likelihood, we conclude that if you're using maximum likelihood estimation, what you like to do is choose the value of theta that maximizes this thing, right? But this first term is just a constant. Theta doesn't even appear in this first term. And so what you like to do is choose the value of theta that maximizes this second term. Notice there's a minus sign there. And so what you'd like to do is, i.e., choose theta to minimize this term, right? Oh, so sigma squared is just a constant, right? No matter what sigma squared is, you know, so if you want to minimize this term, excuse me, if you want to maximize this term, negative of this thing, that's the same as minimizing this term, but this is just j of theta, the cost function you saw earlier for linear regression. Okay, so this little proof shows that choosing the value of theta to minimize the least squares errors, like you saw last Wednesday, that's just finding the maximum likelihood estimate for the parameters theta under this set of assumptions we made, that the error terms are Gaussian and IID. Okay? Yeah, go ahead. Oh, thank you. Yes, great. Yeah, thanks. Yeah, go ahead.
Is there a situation where using this formula instead of the least squares cost function would be a better idea?
Oh, is there a situation where using this formula instead of least squares cost function would be a better idea? No, so this, I think this derivation shows that this is completely equivalent to least squares, right? That if you're willing to assume that the error terms are Gaussian and IID, and if you want to use maximum likelihood estimation, which is a very natural procedure in statistics, then then you should use least squares, right? So yeah.
If you know for some reason that the errors are not IID, like is there a better way? Like would you figure out a better cost function?
If you knew for some reason errors are not ID, we should figure out a better cost function. Yes and no. I think that when building learning algorithms, often we make assumptions about the world that we just know are not 100% true because it leads to algorithms that are computation efficient. And so if you knew that your training set was very, very non-IID, there are more sophisticated models you could build. But but very often we wouldn't bother, I think. Yeah. More often than not, we might not bother. I can think of a few special cases where you would bother, but only if you think the assumptions are really, really bad, and if you don't have enough data and something. Quite rare. All right. Let me think. Boy, all right. I want to move on to make sure we get through the rest of things. Any burning questions? No? Okay, cool. All right. So armed with this machinery, right? So what did we do here was we set up a set of probabilistic assumptions. We made certain assumptions about P of y given x, right? The key assumption was Gaussian errors and IID. And then through maximum likelihood estimation, we derived an algorithm, which turns out to be exactly the least squares algorithm, right? What I'd like to do is take this framework and apply it to our first classification problem, right? And so the key steps are, one, make an assumption about P of y given x, P of y given x parameterized theta, and then second is figure out maximum likelihood estimation. So I'd like to take this framework and apply it to a different type of problem where the value of y is now either 0 or 1. So this is a classification problem. Okay? So let's see. So in the classification problem, in our first classification problem, we're going to start with binary classification. So the value of y is either 0 or 1. And sometimes we call this binary classification because there are two classes. Classification. Right? And so right? So that's a data set where I guess this is x and this is y. So something that's not a good idea is to apply linear regression to this data set. Sometimes people will do it and maybe they'll get away with it, but I wouldn't do it. And here's why, which is it's tempting to just fit a straight line to this data and then take the straight line and threshold it at 0.5 and then say, oh, if it's above 0.5, rounds off to 1. If it's below 0.5, rounds it off to 0. But it turns out that this is not a good idea for classification problems, and here's why. which is, for this data set, it's really obvious what the pattern is, right? Everything to the left of this point predict 0, everything to the right of that point predict 1. But let's say we now change the data set to just add one more example there, right? And the pattern is still really obvious. It's everything to the left of this predict 0, everything to the right of that predict 1. But if you fit a straight line to this data set with this extra 1 point there, and this is not even an outlier, it's really obvious that this point way out there should be labeled 1. But with this extra example, if you fit a straight line to the data, you end up with maybe something like that. And somehow adding this one example, it really didn't change anything, right? But somehow the straight line fit moved from the green line to the moved from the blue line to the green line. And if you now threshold it at 0.5, you end up with a very different decision boundary. And so linear regression is just not a good algorithm for classification. Some people use it, and sometimes they get lucky and it's not too bad, but I personally never use linear regression for classification algorithms, right? Because you just don't know if you end up with a really bad fit to the data like this, okay? And the other unnatural thing about using linear regression for a classification problem is that you know for a classification problem that the values are 0 or 1, right? And so to output negative values or values even greater than 1 seems strange. So what I'd like to share with you now is really probably by far the most commonly used classification algorithm called logistic regression. I want to say the two learning algorithms I probably use the most often are linear regression and logistic regression. Yeah, probably that's true. Yeah, right. This is the algorithm. So as we designed the logistic regression algorithm, one of the things we might naturally want is for the hypothesis to output values between 0 and 1, right? And this is mathematical notation for the values for h of x, or h subscript theta of x, lies in the set from 0 to 1, right? This 0 to 1 square bracket is a set of all real numbers from 0 to 1. So this says we want the hypothesis output values in between 0 and 1, so in the set of all numbers from 0 to 1. And so we're going to choose the following form of the hypothesis. So I'm going to define a function g of z that looks like this. And this is called the sigmoid or the logistic function. These are synonyms. They mean exactly the same thing. So it can be called the sigmoid function or the logistic function. It means exactly the same thing. But I'm going to choose a function g of z. And this function is shaped as follows. If you plot this function, you find that it looks like this, where if the horizontal axis is z, then this is g of z. And so it crosses x-intercept at 0. And it starts off, really, really close to 0, rises, and then asymptotes towards 1. And so g of z outputs values between 0 and 1. And what logistic regression does is instead of, let's see, so previously for linear regression, we had chosen this form for the hypothesis, right? We just made a choice that we'll say that housing prices are a linear function of the features x. And what logistic regression does is theta transpose x could be bigger than 1, it could be less than 0, which is not very natural. But it's going to take theta transpose x and pass it through this sigmoid function g so that it's forced to output values only between 0 and 1. Okay? So, when designing a learning algorithm, sometimes you just have to choose the form of the hypothesis. How are you going to represent the function h, or h subscript theta? And so we're making that choice here today. And if you're wondering, you know, there are lots of functions that we could have chosen, right? There are lots of, why not this function, or why not, you know, there are lots of functions with vaguely this shape that go between 0 and 1. So why are we choosing this specifically? It turns out that there's a broader class of algorithms called generalized linear models. You hear about on Wednesday, of which this is a special case. So we've seen linear regression, you see logistic regression in a second, and on Wednesday you see that both of these examples of a much bigger set of algorithms derive using a broader set of principles. So for now, just, you know, take my word for it that we want to use the logistic function. It'll turn out, you see on Wednesday, that there's a way to derive even this function from more basic principles rather than just pulling out this out of a hat. But for now, let me just pull this out of a hat and say that's the one we want to use. Okay. So, let's make some assumptions about the distribution of y given x parameterized by theta. So I'm going to assume that the data has the following distribution. The probability of y being 1, again, from the breast cancer prediction that we had from the first lecture, right? It would be the chance of a tumor being cancerous or being malignant, chance of y being 1, given the size of a tumor, if that's a feature x, parameterized by theta, that this is equal to the output of your hypothesis. Okay? So in other words, we're going to assume that what you want your learning algorithm to do is input the features and tell me what's the chance that this tumor is malignant, right? What's the chance that y is equal to 1? And by logic, I guess, because y can be only 1 or 0, the chance of y being equal to 0, this has got to be 1 minus that. Right? Because if a tumor has a 10% chance of being malignant, that means it has a 1 minus that. It means it must have a 90% chance of being benign, right? Since these two probabilities must add up to 1. Okay? Yeah. Say that again? Oh, can we change the probability? Yes, you can, but I'm not, yeah, but I think just to stick with convention in logistic regression, yeah, sure. We could assume that P of y equals 1 was this and P of y equals 1 was that, but I think either way, it's just what you call a positive example, what you call a negative example, right? So I want to use this convention, okay? And now, bearing in mind that y, right, by definition, because it's a binary classification problem, but bearing in mind that y can only take on 2 values, 0 or 1, there's a nifty sort of little algebra way to take these two equations and write them in one equation. And this will make some of the math a little bit easier. We're going to take these two equations, take these two assumptions, or take these two facts, and compress it into one equation, which is this. Okay? Oh, and I dropped the theta subscript just to simplify the notation a bit. Right? I'm going to be a little bit sloppy sometimes. Well, a little less formal whether I write the theta there or not. Okay? But these two definitions of P of y given x parameterized by theta, bearing in mind that y is either 0 or 1, can be compressed into one equation like this. And let me just say why. Right? It's because if y, it's a different color. All right. If y is equal to 1, then this becomes h of x to the power of 1 times this thing to the power of 0, right? If y is equal to 1, then 1 minus y is 0. And, you know, anything to the power of 0 is just equal to 1. And so if y is equal to 1, you end up with P of y given x parameterized by theta equals h of x, right? Which is just what we had there. And conversely, if y is equal to 0, then this thing would be 0, and this thing would be 1. And so you end up with P of y given x parameters theta is equal to 1 minus h of x, which is just equal to that second equation. Okay? Right? And so this is a nifty way to take these two equations and compress them into one line, because depending on whether y is 0 or 1, one of these two terms switches off because it's exponentiated to the power of 0. And anything to the power of 0 is just equal to 1, right? So one of these terms is just 1, thus leaving the other term and thus selecting the appropriate equation depending on whether y is 0 or 1. Okay? So with that, so with this little I don't know, notational trick, it'll make the later derivations simpler. Okay? Yeah. So, let me use the new board. I want that. Oh. All right, actually, I can reuse a lot of this. All right, so we're going to use maximum likelihood estimation again. So let's write down the likelihood of the parameters. Well, it's actually P of all the y's given all the x's parameterized by theta, which is equal to this, which is now equal to product from I equals 1 through m, h of xi to the power of yi times 1 minus h of xi to the power of 1 minus yi. Okay, where all I did was take this definition of P of y given x parameterized by theta, from that, after we did that little exponentiation trick and wrote it in here. Right? And then with maximum likelihood estimation, we'll want to find the value of theta that maximizes the likelihood of the parameters. And so same as what we did for linear regression, to make the algebra, to make the algebra a bit more simple, we're going to take the log of the likelihood, and so compute the log likelihood. And so that's equal to, let's see, right, and so if you take the log of that, you end up with that. Okay? And so in other words, the last thing you want to do is try to choose the value of theta to try to maximize L of theta. Okay? Now, so just to summarize where we are, right? If you're trying to predict malignancy and benignness of tumors, you'd have a training set with xi, yi. You define the likelihood, define the log likelihood, and then what you need to do is have an algorithm, such as gradient descent or gradient ascent, talk about that in a sec, to try to find the value of theta that maximizes the log likelihood. And then having chosen the value of theta, when a new patient walks into the doctor's office, you would take the features of the new tumor and then use h of theta to estimate the chance of this new tumor in a new patient that walks in tomorrow, to estimate the chance that this new thing is malignant or benign. Okay? So the algorithm we're going to use to choose theta to try to maximize the log likelihood is a gradient ascent or batch gradient ascent. And what that means is we will update the parameters theta j according to theta j plus the partial derivative with respect to the log likelihood. Okay? And the differences from what you saw for linear regression from last time is the following. Just two differences, I guess. For linear regression, last week I had written this down. Theta j gets updated as theta j minus partial with respect to theta j of j of theta, right? So you saw this on Wednesday. So the two differences between that is, well, first, instead of j of theta, you're now trying to optimize the log likelihood instead of the squared cost function. And the second change is, previously you were trying to minimize the squared error. That's why we had the minus. And today you're trying to maximize the log likelihood, which is why there's a plus sign. Okay? And so, so gradient descent, is trying to climb down this hill, whereas gradient ascent has a concave function like this, and it's trying to climb up the hill rather than climb down the hill. So that's why there's a plus symbol here instead of a minus symbol, because it's trying to maximize the function rather than minimize the function. So the last thing to really flesh out this algorithm, which is done in the lecture notes but I don't want to do it here today, is to plug in the definition of h of theta into this equation, and then take this thing. So that's the log likelihood of theta. And then through calculus and algebra, you could take derivatives of this whole thing with respect to theta. This is done in detail in the lecture notes, so I don't want to do this in class. But go ahead and take derivatives of this big formula with respect to the parameters theta in order to figure out what is that thing, right? What is this thing that I just circled? And it turns out that if you do so, you will find that Bash gradient ascent is the following. You update theta j according to, oh, actually, I'm sorry, I forgot the learning rate. Yeah, it's for learning rate alpha. Okay, learning rate alpha times this. Because this term here is the partial derivative with respect to theta j of the log likelihood. Okay, and the full calculus and so on derivation is given in the lecture notes. Okay, yeah. Is there a chance of local maximum in this case? No, there isn't. It turns out that this function, the log likelihood function, L of theta, for logistic regression, it always looks like that. So this is a concave function. So there are no local, the only maximum is the global maximum. That's actually another reason why we chose the logistic function, because if you choose the logistic function, rather than some other function going from 0 to 1, you're guaranteed that the likelihood function has only one global maximum. And there's actually a big class of algorithms. Actually, what you see on Wednesday is there's a big class of algorithms, of which linear regression is one example, logistic regression is another example, and for all of these algorithms in this class, there are no local optima problems when you derive them this way. So you see that on Wednesday when we talk about generalized linear models. Okay. So actually, before I take your questions, just one question for you to think about. This looks exactly the same as what we figured out for linear regression, right? Like when actually the difference for linear regression was I had a minus sign here, and I reversed these two terms. I think h theta of xi minus yi. If you put the minus sign there and reverse these two terms, so take the minus minus, this is actually exactly the same as what we had come up with for linear regression. So why is this different, right? I started off saying don't use linear regression for classification problems because of that problem that a single example could really, So I started off with an example showing that linear regression is really bad for classification, and we did all this work and came back to the same algorithm. So what happened? Yeah, go ahead.
Your h of theta is nonlinear now?
Yeah, all right, cool, awesome, right? So what happened is the definition of h of theta is now different than before, but the surface level, the equation turns out to be the same, okay? And again, it turns out that for every algorithm in this class of algorithms you see on Wednesday, you end up with the same thing. Actually, this is a general property of a much bigger class of algorithms called generalized linear models. although, yeah, interesting historical divergence. Because of the confusion between these two algorithms in the early history of machine learning, there was some debate about, between academics saying, no, I invented that, no, I invented that. But, and then the conclusion was, no, it's actually different algorithms. Right? All right, any questions? Go ahead. Oh, great question. Is there equivalence to normal equations to logistic regression? Short answer is no. So for linear regression, the normal equations gives you like a one-shot way to just find the best value of theta. There is no known way to just have a closed form equation that lets you find the best value of theta, which is why you always have to use an algorithm, an iterative optimization algorithm, such as gradient ascent, or we'll see in a second, Newton's method. All right, cool. Question. So, there's a great lead into the last topic for today, which is Newton's method. Gradient ascent, right? It's a good algorithm. I use gradient ascent all the time, but it takes a baby step, takes a baby step, takes a baby step, takes a lot of iterations for gradient ascent to converge. There's another algorithm called Newton's method, which allows you to take much bigger jumps to let theta, there are problems where you might need, say 100 iterations or 1,000 iterations of gradient ascent, that if you run this algorithm called Newton's method, you might need only 10 iterations to get to a very good value of theta. But each iteration will be more expensive. We'll talk about pros and cons in a second. But let's see let's describe this algorithm, which is sometimes much faster for than gradient ascent for optimizing the value of theta. Okay? So what we'd like to do is, all right. So let me use the simplified one-dimensional problem to describe Newton's method. So I'm going to solve a slightly different problem with Newton's method, which is, say you have some function f, right? And you want to find theta such that f of theta is equal to 0. Okay, so this is a problem that Newton's method solves. And the way we're going to use this later is, what you really want is to maximize L of theta right? And well, at the maximum, the first derivative must be 0. So i.e., you want a value where the derivative L prime of theta is equal to 0, right? And L prime is the derivative of theta. I guess this is, right, L prime is another notation for the first derivative of theta. So if you want to maximize a function or minimize a function, what that really means is you want to find a point where the derivative is equal to 0. So the way we're going to use Newton's method is we're going to set f of theta equal to the derivative and then try to find a point where the derivative is equal to 0. Okay? But to explain Newton's method, I'm going to work on this other problem where you have a function f and you just want to find the value of theta where f of theta is equal to 0. And then we'll set f equal to L prime theta, and that's how we'll apply this to logistic regression. Okay. So let me draw in pictures how this algorithm works. All right. So let's say that's the function f, and to make this drawable on a whiteboard, I'm going to assume theta is just a real number for now. So theta is just a single, like a scalar, a real number. So this is how Newton's method works. Oh, and the goal is to find this point, right? The goal is to find the value of theta with f of theta is equal to 0. Okay. So let's say you start off let's say you start off at this point, right? At the first iteration, you know, random initialized theta or initialized theta 0 or something, but let's say you start off at that point. This is how one iteration of Newton's method will work, which is, actually, let me use a different color. Right, start off with theta 0, that's just the first value, first iteration. What we're going to do is look at the function f, and then find a line that's just tangent to f. So take the derivative of f and find a line that's just tangent to f. So take that red line, that just touches the function f. And we're going to use, if you will, use a straight line approximation to f and solve for where f touches the horizontal axis. So we're going to solve for the point where this straight line touches the horizontal axis. Okay? And then we're going to set this, and that's one iteration of Newton's method. So we're going to move from this value to this value. Okay? And then in the second iteration of Newton's method, we're going to look at this point, and again, you know, take a line that's just tangent to it, and then solve for where this touches the horizontal axis, and then that's after two iterations of Newton's method, right? And then you repeat. Take this. Sometimes you can overshoot a little bit, but that's okay, right? And then that's, I guess I'll cycle back to red. That's theta 3. Then you take this. That's theta 4. Excuse me. So you can tell that Newton's method is actually a pretty fast algorithm, right? When in just, what, 1, 2, 3, 4 iterations, we've gotten really, really close to the point where f of theta is equal to 0. So let's write out the math for how you do this. So let's see. So let me just write out derive, you know, how you go from theta 0 to theta 1. So I'm going to use this horizontal distance. I'm going to denote this as delta. This triangle is uppercase Greek alphabet delta, right? This is lowercase delta, that's uppercase delta, right? And then the height here, well, that's just f of theta 0, right? Since the height is just f of theta 0. And so, let's see. Right. So what we like to do is solve for the value of delta, because one iteration of Newton's method is to set, you know, theta 1 is set to theta 0 minus delta, right? So how do you solve for delta? Well, from calculus, we know that the slope of the function f is the height over the run, right? Height over the width. And so we know that the derivative of f prime, that's the derivative of f, at the point theta 0, that's equal to the height, that's f of theta, divided by the horizontal, right? So the derivative, meaning the slope of the red line, is by definition of derivatives, is this ratio between this height over this width. And so delta is equal to f of theta 0 over f prime of theta 0. And if you plug that in, then you find that a single iteration of Newton's method is the following rule. Theta t plus 1 gets updated as theta t minus f of theta t over f prime of theta t. Okay? Where instead of 0 and 1, I replaced it with t and t plus 1. Right? And finally, you know, the very first thing we did was let's let f of theta be equal to, say, L prime of theta, right? Because we want to find the place where the first derivative of L is 0. Then this becomes theta t plus 1 gets updated as theta t minus L prime of theta t over L double prime of theta t. So it's really the first derivative divided by the second derivative. Okay. So Newton's method is a very fast algorithm, and it has, Newton's method enjoys a property called quadratic convergence. Not a great name, don't worry too much about what it means, but informally what it means is that if on one iteration, Newton's method has 0.01 error, so on the x-axis you're 0.01 away from the value, from the true minimum of the true value of f is equal to 0. After one iteration, the error could go to 0.0001 error. And after two iterations, it goes 0, 0, because 0, 0. Right. But roughly, Newton's method, under certain assumptions that function is smooth, not too far from quadratic, the number of significant digits that you have converged to the minimum doubles on a single iteration. So this is called quadratic convergence. And so when you get near the minimum, Newton's method converges extremely rapidly, right? So after a single iteration, it becomes much more accurate. After another iteration, it becomes way, way, way more accurate, which is why Newton's method requires relatively few iterations. Let's see. I have written out Newton's method for when theta is a real number. When theta is a vector, right? Then the generalization of the rule I wrote above is the following. Theta t plus 1 gets updated as theta t plus h that, where H is the Hessian matrix. So these details are written in the lecture notes. But to give you a sense, when theta is a vector, this is a vector of derivatives. Right, so I guess this is Rn plus 1 dimensional. If theta is an Rn plus 1, then this derivative with respect to theta of the log likelihood becomes a vector of derivatives. And the Hessian matrix, this becomes a matrix that's Rn plus 1 by n plus 1. So it becomes a squared matrix with the dimension equal to the parameter vector theta. And the Hessian matrix is defined as the matrix of partial derivatives. Right, so, and so the disadvantage of Newton's method is that in high dimensional problems, if theta is a vector, that each step of Newton's method is much more expensive because you're either solving linear system equations or having to invert a pretty big matrix. So if theta is 10-dimensional, this involves inverting a 10 by 10 matrix, which is fine. But if theta was 10,000 or 100,000, then each iteration requires computing like 100,000 by 100,000 matrix and inverting that, which is very hard, right? It's actually very difficult to do that in very high dimensional problems. So, some rules of thumb, if the number of parameters you have for if the number of parameters for logistic regression is not too big, if you have 10 parameters or 50 parameters, I would very likely use Newton's method because then you probably get convergence in maybe 10 iterations or 15 iterations or even less than 10 iterations. But if you have a very large number of parameters, if you have 10,000 parameters, then rather than dealing with a 10,000 by 10,000 matrix or even bigger than 50,000 by 50,000 matrix, if you have 50,000 parameters, I would use gradient descent instead. Okay, but if the number of parameters is not too big, so that the computational cost per iteration is manageable, then Newton's method converges in a very small number of iterations and can be a much faster algorithm than gradient descent. All right. So that's it for Newton's methods. On Wednesday, I guess I'm running out of time. On Wednesday, you hear about generalized linear models. I think, unfortunately, I promised to be in Washington, D.C. Tonight, I guess, through Wednesday. So you hear from I think Anand will give the lecture on Wednesday, but I will be back next week. So unfortunately, he was planning to do this, but because of his health things, he can't lecture. So Anand will be doing this Wednesday. Thanks, everyone. See you on Wednesday.